We're now going to take equilibrium constants one step further and derive the most general kind of equilibrium constant, which is valid for all systems, whether they behave with any kind of ideal behavior or not. So first thing we want to do is define the chemical potential, which is the molar Gibbs energy, which, as we know, is the important quantity of interest for chemical equilibrium because Gibbs energy determines where equilibrium lies for any given chemical reaction. So our chemical potential is equal to some standard chemical potential of this species I, some undetermined chemical species, plus gas constant times temperature times natural log of its activity. So the quantity of interest, which is most general, which tells us how the chemical potential changes under varying conditions of concentration, pressure, etc., is going to be its activity. Okay, and as we said, this is the most general equation for a general system. This is valid for the chemical potential of all systems, whether ideal or not. So to remind ourselves, some values of activity which we have for some different various systems. We have the activity goes to the mole fraction as mole fraction goes to 1 if you're defining your activity constant in terms of mole fraction. And there, the standard chemical potential is just equal to the chemical potential of the pure substance. So this was for solutions and primarily for solvents in liquid-liquid solutions and liquid-solid solutions that we saw this type of activity coefficient. We can also have activity defined in terms of molality, and we can have activity defined in terms of molarity, both measures of concentration of solutes. So the activity coefficient goes to molarity as the molarity of a solute goes to 0, and it goes to also the concentration as the concentration goes to 0, depending on whether you defined it in terms of molality or molarity. And here, our standard chemical potential there is equal to the chemical potential evaluated at 1 mole, so 1 mole of solute per kilogram of solvent. And in terms of molarity, we have our standard chemical potential is defined as the chemical potential at 1 molar, at 1 mole of solute per liter of solution. Again, important to define the proper standard state for every system because chemical potential and Gibbs energy has no meaning unless it's well defined what the 0 condition is. So what the standard state where you have 0 chemical potential is. Okay, so in order to generalize this, these type of solution quantities in terms of the reactions of gases, which we've been primarily talking about thus far, we need to generalize and define what the activity of a gas is. So for gases, we're going to define that the activity of a gas is its fugacity divided by standard fugacity. So we remind ourselves that standard fugacity is standard pressure, which is 1 bar. So I'll say that standard fugacity equals standard pressure, which is equal to 1 bar. But now for ideal gases, fugacity just becomes pressure. But the nice thing about having defined this is having defined activity in this way for all types of systems. This works for solids, liquids, solutes, gases, everything, is that we have all phases are on the same footing relative to defining their chemical potential and thus the Gibbs energy and chemical equilibrium. So we can move forward here and start defining the reaction Gibbs energy for any most general type of system that we can imagine chemically. So let's define our Gibbs energy of reaction. is going to equal the standard Gibbs energy of reaction plus RT. And if we have some hypothetical reaction that I have defined, nu AA plus nu BB. Again, this reaction just being used as an example throughout this series on chemical equilibrium. So the capital letters being chemical species and the nus being their stoichiometric coefficients. We have not specified the state this time because it's now irrelevant what the state is. It doesn't matter what state they are because we have defined activities for all states of matter. So our equation for the reaction energy is now general for any type of phase that we can give. And that's going to be activity of C times to the power of its stoichiometric coefficient, nu C, activity of D to the nu D, activity of A to nu A, activity of B to the power of nu B. Okay, and this equation for the Gibbs energy of reaction is named after the famous thermodynamicist G.N. Lewis. So this is called the Lewis equation. And this is general for any type of chemical system which we can imagine. So in terms of our reaction quotient, now we have defined our activity quotient. Our reaction quotient, when defined in terms of activities, we call an activity quotient, and that would be QA in terms of activities, which is the quantity in parentheses which we defined there, which again has products on top and reactants on bottom. So the Gibbs energy of reaction for the most general type of chemical system, replacing in this value up here, Gibbs energy equals standard Gibbs energy plus RT log QA, reaction or activity quotient for our given reaction. And so our standard Gibbs energy of reaction for the most general case is equal to minus RT log Ka of T, where our equation here for Ka again being another thermodynamic equilibrium constant because it's true for non-ideal systems as well. The equilibrium constant in terms of activities, the thermodynamic equilibrium constant is just our activity quotient evaluated at equilibrium.